Hello, all, and welcome to Artham Academy, aspiring leaders in innovation and technology. In today's video, we would talk about shear force and bending moments. We would also see shear force and bending moment diagrams with the help of an example. We will have a brief overview about the shear force and bending moment diagrams of some common examples which are very useful. So let's get started.
Now let's discuss about the importance of SFD and BMD. Shear force diagrams and bending moment diagrams are the analytical tools used to perform structural design. For the designing, this SFD and BMD are actually very important. It gives us an idea or the load, how much load the beam is taking and what are the dimensions that we have to take. So it is very essential for us to know. These diagrams can be used to easily determine the type, size and material of a member in a structure to support loads without structural failure. Another application of shear and bending moment diagram is that the deflection of the beam can be easily determined. You would have seen a lot of ways through which the deflection is being calculated. There is one Castigliano method, there is moment area method, there is normal conjugate beam method, and there are n number of ways how we can calculate. In moment area method, you actually need the BMD for calculation. So SFD and BMD are an important part of any designing that is happening on the beam. It has to be calculated, and through which the stresses has to be calculated, and through which we know whether the material will be able to sustain that amount of load or not. So it is actually very important. Now shear force. Shear force at any section is equal to the algebraic sum of transverse forces either to the left or the right of the section. It means if we consider a beam and it has a number of forces, whether it's a uniform varying load, uniform distributed load and a point load, we have to just add up whether it's positive and negative, and whatever is the resultant force, that is the shear force that is acting on that. Obviously there is going to be variation from one place to other along the span of the beam, and that is what we are going to learn in the SFD. SFD is a graphical representation of the variation of shear force along the length of the beam. That is, it varies from one place to another because at every section there is a different algebraic sum, and at the end it becomes equal to the reaction force, and that is how we get to know that our shear force diagram is correct. If it not, then there is some calculation error that you are making. Force acting in the right hand side of the section in the upward direction is taken as negative, whereas force in the right hand side of the section in downwards direction is taken as positive. So these are the two sign conventions that we are following and we will be following in our video, so that you take a note of it. It would help you to understand the example that we would be covering today. Shear force diagram. Obviously I told you it's a variation of the shear forces at each and every section. There are some of the common shapes that we usually encounter in the shear force diagram, like a trapezium, like a rectangle, like a triangle. So these are some of the most common SFDBMDs. Now let's talk about the bending moment. The moment of the force or the distance about which the tendency of rotation is observed is known as bending moment. For example, if I fix a log at one end and try to rotate or try to pull it from the other end, keeping the other end fixed, I am giving a moment. That is the load that I am giving, and from the distance. Bending moment is very common in our daily lives. We can take references easily. So bending moment diagram is a graphical representation of variation along the length of the beam. BMD is the graphical representation of the variation of bending moment along the length of the beam. Each and every section there would be some different bending moments, and that is being calculated and that is being plotted along the span. BMD also has some sign conventions that we'll be following. BMD that causes concavity upwards, or also known as sagging, will be taken as positive, and BMD that causes convexity upwards is taken as negative, which is also known as hogging. Bending moment diagram, it is like the same thing, the variation that has been taking place from one place to another at each and every section. These are the common shapes that we usually see in the bending moment diagrams. And as I told, sagging is taken as positive and hogging is taken as negative. Now let us try to do a model so that you would get an idea what is the shear force diagram and what is the bending moment diagram. So let us look at this beam This is a beam which is simply supported. Simply supported means it is supported at both the ends. One end is fixed and other end is roller. This is the usual way of making a simply supported beam in the real world scenario as well. We are applying a point load or a concentrated load at the middle of the beam. And this is the shear force diagram and the bending moment diagram that we are getting. First of all, we would calculate the reactions. Obviously, from the symmetry, we can see that if F load is applied at the center, there should be an opposite F load to balance so that its state should not change. And that is given by the reactions. That is F by 2, F by 2. Since it is a symmetric case, the reactions become equal. And that's why we see such of symmetry in the shear force diagram as well as in the bending moment diagram. In the shear force diagram, as I already told, that the upward forces as coming from the right, we would take it as negative, and the downward force we would be taking as positive. So as we go from here, we would say this is negative. So there is a negative force minus F by 2. Since we are going from this to this, there is a sudden force that F is coming, and suddenly there is a jump from there to here. And we see that F by 2 is calculated. You can also verify that F by 2 is same as this, that F minus F by 2. So it is giving us the same reaction. We can always verify whether our shear force diagram or bending moment diagrams from the basic conventions. Anyway, I'll be covering it in the tips section of this video. Now talking about the derivation. Let's look at the derivation. So if we see that there are two reaction forces at point A and C, if we go back, we see A and C are the 2 points where reaction is taking place. That's why we have taken RA and RB. And the other equation that we need is taking a moment about A. So this is the moment. This is the section through which we would be taking the moment. And we would see that if we take this as the reference, F into L by 2, this is the moment that we are getting in this way, that is in the clockwise direction. And in the anti-clockwise direction, we are getting a moment of F by 2 into L. Okay. And that is how we calculate it. So that is how we calculate the force and the reaction. So since we know the reaction, that is RA is equals to and RC is equals to F by 2, we now try to do our variation of the shear force diagram and the bending moment diagram. We create a general function that is Vx, x as in any distance which we take from right to left. So if we take x is equals to 0 also, this would be same, because in this entire section from B to C, the F by 2 is constant. So if we cut a section here, we would always get that in the right side we have F by 2. And this is the force that we would be getting. That's why in the general Vx section we have got minus Rc. Whereas in the moment section we can see there is a x term that is coming. So it depends on the value. So it will be varying linearly. We can get an idea from that because x has a power of 1. So mx is equals to rc into x, which means that at x is equals to 0, this would be 0. That gives us another hint that at the supports, there would be a 0 moment. So it gives us another hint to cross verify whether we have drawn our SFDBMD correctly or not. So this is the moment that we would be getting in the section BC. Now talking about AB, if we move ahead, there is one, if we cut a section from this way between AB, there is one downward force, positive downward force, because we are moving from right to left according to the sign conventions that we have assumed. And also to tell you in the middle only that you can always take any sign convention, it's up to you, but it's preferred that you follow this convention because it is accepted in the books and it would not confuse you. So if we take a section from here, F is here and then minus F by 2 is here. So this way we get a net force of F by 2. And that is how we cross-verify that there is a plus F by 2 here. And that solves our problem that we are doing our shear force diagram correctly. So with the introduction of this force, this suddenly shoots from here to here and becomes F by 2. Now talking about the moment in the section A and B, we take RC is equals to X. We take Mx is equals to RC into X minus F times X minus L by 2. Now I would explain you this equation. If we come at this section, we can see that there is one RC into some distance of L, and it is trying to rotate it this way. It is trying to rotate in the anti-clockwise direction. That is how sagging happens. But now if we come in this way it is causing sagging, but in this way, because it is moving in the clockwise direction, it is causing hogging. And that's why this hogging is taken as negative in our equation. That's why we are taking a value only this much, only the section between the cut section here to the point of the application. That's why we are saying that X minus L by 2 means this BC portion has to be excluded. And that is the whole equation. I hope you would have got it. Now let's talk about the basic examples of SFD and BMD. We can see that there are three types of bend. One, concentrated loading, another uniformly distributed loading, and another uniformly varying loading. These are the different cases that usually happens and have been categorized in one. You can see the shear force diagram, the linear diagram, the parabolic diagram. You can see the shear force diagram of these loadings and also the moment diagrams, bending moment diagrams of these values. You would clearly notice one thing, that the slope keeps on increasing. For example, this constant becomes linear, this linear becomes parabolic, this linear becomes parabolic, and this parabolic becomes cubic. It means that with the application of the loading in this way, from point load to constant to linear, there is increase in the slope. There is increase in the degree of the slope, that is from 0, 1 and 2. You can just make a note of it. It's actually very helpful while solving problems, while analyzing beams. Now if you talk about some more beams, this is the beam which has a moment, only a moment, and this is how the beam looks like, and this is how the shear force diagram looks like, a constant, because there is no load, there is concentrated load, and we can see that the degree increases from 1 to 1, from 0 to 1 here. The slope increases from 0 to 1, and this is always applicable. It gives you an idea and kind of thing so that you can always cross verify. Now in this also you see that there is one concentrated load. That's why we are getting a slope of 0, and in the moment diagram we are getting a slope of something, that is a linear slope. In the constant, whereas in the constant load, these we are talking about the cantilever beams for your information. In the shear force diagrams we can see that this is linear, where this is parabolic, so the degree increases. Now some of the tips that I was talking about, SFD and BMD. Consider either left or the right hand side of the section. Add forces normal to beam on one of the side. For example, right hand side chosen, force acts downward in the positive and force acting upwards is taken as negative. The positive values of the SFD and BMD are plotted above and the negative values below the baseline. This is very basic that we saw in our example as well, that there is negative value that is going below the baseline and there is positive value that is going above the baseline. SFD will decrease or increase suddenly due to vertical point load. Yes, this is a very important point and you should always make a note of it, because if you make a mistake something like this, you would instantly hit that there is a concentrated load. There should be a sudden jump because of the vertical load, and that is also applicable for BMD as well. In BMD, if there is a sudden moment, if there is a concentrated moment, you can see in the previous, if there is a concentrated moment here, you would see a sudden jump, and that is the method of verifying it. Shear force between any two vertical loads are constant and represented as horizontal. This is also a very baseline that you should know, that if you are taking any section and it remains constant, then it's a horizontal value because the value remains same. Bending moment at two supports of a simply supported beam and also at the free end of the cantilever beam will be 0. This we actually verified because we saw that mx is equals to rc into x. So x is the value that we are moving away from that certain point. But if we are not even moving, so x will remain 0, and that's why the mx will remain 0. So this is the method of verifying it. For more reference, you can visit these websites. This will give you a better insight. We have covered briefly what is shear force diagram and what is bending moment diagram, but you want to get more deep into it, you should definitely visit these websites. This will give you a better insight.
That's all for today. I hope that you would have loved this video. For any information, you can contact to given below details and feel free to reach to us. Thank you.